All right, so in this lecture we'll talk about energy minimization. And also universal optimality. And the idea is some of the ingredients for this proof of universal optimality. You'll see some modular form showing up in Mahesh's lecture, which is the next one. And tomorrow, then we'll try to sketch a proof of universal optimality. And today, if I have time, I'm going to try to sort of sketch the proof of the sphere packing, the magic functions, as much as I can without actually assuming that you know anything about modular forms. So try and do something like that. Okay. Okay, so recall the setup for codes for energy. So I'm going to change it very slightly. So I think I may have said that f was a function, f was defined on inner products between points, but the normal procedure is to, the normal definition is to define it on the distance between points. So if you have 2 points on the sphere, in the unit sphere, the distance can be anywhere between 0 and 2. The other way around, I guess. R, potential function. Then for the code in Sn-1, defined EF of C equals sum over x and y and c, x not equal to y, f of x minus y. Just the distance between, the chordal distance between 2 points on the sphere. So this is called the potential energy of C with respect to f, potential function f. Okay, so this is just the chordal, the Euclidean distance embedded inside Rn. And I'll just make a connection to what I might have said before. So since the chordal distance squared is 2 minus twice the inner product, because these have norm 1, so we can change it to a function of inner product. Again, change it to a function of inner product. So it's sort of, I can give an alternative definition, which as I did last time, I think I might have defined it in terms of inner product. But this is the standard usage. Okay, so all right, so so basic question is the following: find the global minimum, find the C that globally minimizes the potential function given the number of points. Okay, so given number of points. So subject to the constraint that C has size n, find the thing that minimizes the potential energy given the number of points n, the ambient dimension small n, and potential function f. Okay, and the usual potential functions, kinds of potential functions we consider are things like inverse power laws of the distance. Although people do consider, in physics, in Euclidean space, people consider sort of slightly more complicated functions too sometimes, like there's something called the Leonard-Jones potential, which can describe interaction between, I think, the electron in the nucleus or something like that, and it sort of dips below and then comes back up, and it involves 1 over r to the 6th and 1 over r to the 12th with 1 positive and 1 negative coefficient. So as you get interaction. Anyhow, normally we will just consider sort of pure repulsive functions, which look like this. Okay, so example. So the best way to see what's going on when you try to solve this problem is to see some examples. So let's see some examples. So what happens for dimension equals 2? So whatever number of points you put, for normal potential functions, you always get a regular n-gon. Okay, so get regular n-gon global minimum. Right, so you get the n vertices of a regular n-gon, minimizing on the circle, minimizing the potential energy. Okay, so what happens when dimension equals 3? So you can look at the numbers of some small numbers of points. So suppose the number of points is 4, then you get, if the number of points is too small, then you basically reduce to a lower dimensional case. So if the number of points is only 3, then everything lies on the equator and you get an equilateral triangle. You reduce to the dimension 2 case, really. So the dimension of number of points is 4, you get a regular tetrahedron. Tetrahedron. And that's a nice symmetric configuration. It tends to always minimize any reasonable potential function that you give it. Okay, but already at n equals 5, so already interesting behavior is seen. Namely, what you get is you get two competing configurations. So one is the triangular bipyramid, which is this. So you get 3 points on the equator and the North Pole and the South Pole. Okay, so that's, of course you have a, when you're computing energy, you need to take all pairs of distances into account. So anyway, so that's the triangular bipyramid. Think triangle at the equator and equilateral triangle at the equator, north and south pole. And then configuration B is the square pyramid. So this is what you observe computationally if you actually try to do gradient descent or something, some computational experiments, and that's what you get. Some things are provable, like these two things are actually provable. For any inverse power law, you will get this. I'll indicate how that's proved. But computationally, this is what you seem to observe. So the square pyramid is the following thing. So you have the North Pole, and then you have a square at some latitude in the southern hemisphere, you have a square. Okay, so square located at latitude theta, some theta in southern hemisphere. Okay, so and the North Pole. So that's 5 points, and that's a competing configuration. And this is actually a family of configurations. So this is really a continuous family. B sub theta, let's say. So what happens? So one thing that I may not have mentioned yet is if you take inverse power laws and you let the power go to infinity, then it essentially becomes a spherical code problem. Because what happens is the only thing that matters is the smallest distance, because if you look at the ratio of the smallest to the next distance, you get, sort of R0 over the other R, which is bigger than R0, to some very high power. So that doesn't matter anymore. I mean, it doesn't contribute. So the only thing that matters, if K is very, very, very large, is the smallest distance. So it becomes a spherical code problem. You just want to separate them out so that they're as far apart as possible. And we do know the answer to the spherical code problem in the 5-point case. In fact, both of these optimize. So the spherical code, here the minimal angle you're going to see is the angle between this and anything on the equator, which is 90 degrees, as well as what happens is this thing comes all the way up to the equator, and you still get 90 degrees. Okay? If you let it be in the southern hemisphere, then the spherical angles between 2 points in the square will be smaller, and that you don't want that for the spherical code problem. Okay, so in some sense, this degenerates to that square pyramid with the square on the equator when k goes to infinity. Okay, but so if k is very large, it's a good question which one wins. And let me just tell you what the answer is. This is a computational answer, not proven. So for inverse power laws, the configuration A wins for small k, for k less than, I think, 7.524 dot dot dot, and B, some B theta wins for larger k. So it's either one or the other. This is not proven. This is expected to be the case, not proven. Proven except for, I believe, k equals 1 and 2, which were proven recently by some massive computer experiments, computer-aided proof by Rich Schwartz at Brown. And in which case he proved, since this is less than 7 point whatever, A wins for these inverse power laws, 1 over r and 1 over r squared. Okay, but if you wanted to prove that the appropriate B theta wins for some large k, that's an open problem. Okay, so this is open and quite. Just a simple question like this is open. N equals 6. You go back to always getting a regular octahedron. N equals, sorry, this is capital N equals 6. Capital N equals, sorry, capital N is the number of points, small n is the dimension. So I should have said capital N. So capital N equals 7 is more complicated. I'm not going to say you get a square and a triangle, or you get, anyway, there are various things. N equals 8. You always get a skew cube. This is another very interesting case, which is open, or also called a square antiprism. What does that look like? So you might think it's going to be a cube because a cube is a regular solid, but it's not a cube because it turns out the square faces are actually not that good for potential energy. So the potential energy twists the two faces, and so what happens is you get a square in the northern hemisphere, and you get the same size square twisted 45 degrees respect to it in the southern hemisphere. So it's a sort of it's a skew cube. Anyway, you can draw the picture, but there's this is again a one-dimensional family. If this is at some theta in the northern hemisphere, latitude theta, this will be at latitude minus theta. So again, one-dimensional family, depending on angle, on latitude. And this is expected to always optimize. For every inverse power law, this family is supposed to be the global optimum. This is open. So when I said you always get this numerically, but this is an open problem. And so on, you can do, the only other sort of very interesting case is n equals 12, you always get a regular icosahedron. But for n equals 20, for instance, you do not get a regular dodecahedron because, again, the pentagonal faces are sort of bad for energy, so you actually get something else. But you've seen that there are some configurations which always optimize potential energy, like the regular octahedron, regular icosahedron, regular tetrahedron, and those are called universally optimal. So let me make a proper definition. So for some isolated examples, one configuration optimizes all such energies 1 over r to the k, right? In fact, it's slightly more general, class of potentials. So let me define what that is. So definition, so a completely monotonic function f of x is one for which for every k, the kth derivative has alternates in sign. Okay, so for all x in the domain. Okay, so in other words, if k is 0, it's saying f itself is non-negative. If k is 1, it's saying f prime is negative, so f is decreasing. So it's a non-negative function, it's decreasing, it's going to be convex, and whatever the natural extension of that is. Okay, so all derivatives alternate in sign. This is something that analysts actually have studied, so it's not completely out of the blue. So you say, right, that f of r is a completely monotonic function of squared distance. If the obvious thing, if f of r is g of r squared for some g which is completely monotonic. Okay. So these are the functions that we'll try to optimize, namely completely monotonic functions of squared distance. So let me just make a little note before I do that. So this is to say that something is a completely monotonic function of squared distance is equivalent to being an absolutely monotonic function of inner product. Okay, so completely and absolutely might sound like synonyms, but apparently they're not for analysts. So absolutely means that all derivatives have the same sign, and that's it's greater than or equal to 0. Okay, so all derivatives are non-negative. That's what. So I won't write it down, but that's what absolutely monotonic is, and that's because f of x. So since if I have f of x, if x is 2 minus 2t, just like over there, so x is r squared, which is 2 minus 2t, so x is related to t by a change of variable which flips the sign, then so g so then is completely monotonic if and only if g of t is f of 2 minus 2t is absolutely monotonic, right? Which is sort of obvious. Okay, so i.e. gkt is greater than 0 for all k and all t. Okay. All right, so let me just now make the definition that something is universally optimal. Say C is universally optimal if it minimizes potential energy for all completely monotonic functions of squared distance. So that's what universally optimal is. Okay, so there are examples, namely I've listed some for you, but let me make a large table of examples. Some examples. And this table you can see in my paper with Henry Cohn, universally optimal distributions of points on spheres. Okay, so I'm going to write down the dimension, the number of points, and they're all going to be designs of some sort. Yeah. A little bigger. Oh, okay, sorry. Yeah. Number of points, this is the strength of the design. The possible inner products and the name of the configuration. Okay, so let's make a little table or a large table. So So first thing is, if the dimension is 2, I already said that for any number of points, you always get the regular n-gon. The regular n-gon is an n-1 design, which is great. The inner product, the possible inner products are cosine of 2 pi j over n, for 1 being n over 2. So in particular, there's about n over 2 of them, and you see that it's a sharp configuration in the sense that I mentioned last time. Okay, the design strength is about twice the number of inner products, and this is just the regular n-gon. I'll drop regular from now on because everything is regular. Okay, so and then if you have any dimension, you always have, and the number of points is sort of small, then you basically lie inside a smaller dimensional sphere, and the design strength is 1, and the only inner product is -1 over n-1, it's the regular simplex. But it's a lower dimensional regular simplex, and then the correct dimensional regular simplex has n+1 points, and the design strength is 2, and here capital N is n+1, so you just get -1 over n, and this is the simplex. Then you have another infinite family, namely the cross polytopes, which is the dual of the cube. So 2n points, namely take the north pole and the south pole, and so go along every axis, take the coordinate vector and it's negative. This is a 3 design. The inner products are -1 and 0. So again, the number of inner products is 2, and twice 2 minus 1 is 3, which is okay. And this is a cross polytope. Then, okay, then let's look at some special configurations. So there's 3, 12 regular icosahedron. It's a 5 design. The inner products are -1 and ±1 over the square root of 5. Icosahedron. And there's the analog of this in the next dimension, which is called the 600 cell. It's got 120 points, 600 faces. It's an 11 design, -1 ±1/2, 0 ±1 square root of 5 over 4. Okay, so there's 4, 5, 6, 7, 8. So this is not enough of a, right? This is not enough of a design. However, this is a special configuration, and it has some other tricks that you can use to show that it's actually universally optimal. So I'm not going to talk about that, but one can show. Okay, then, okay, let's start with the E8 family. So then there's 8, 240, the minimal configuration of the E8 lattice. It is a 7 design. The inner products are -1 ±1/2 and 0, and E8 roots. Then there is, if you take its kissing configuration, 7, I think I already listed this last time. It's a 5 design, -1 ±1/3. This is the kissing configuration of the previous one. Then you take the kissing configuration of that, you get the Klepsch one, Schläfli. I think this Schläfli configuration, 627. It's a 4 design, -1/2 and 1/4. Kissing. Take the kissing configuration of that, you get 5, 16, 3, -3/5 and 1/5. Kissing. Then you can start with the Leach lattice, 196, 560. If you take the kissing of this, you get the 410 1/6 one that I talked about with the SDV bounds. So that's optimal as a code, but I don't know if that's universally optimal. I'm not sure if that's known. This is 11 design, -1 ±1/2 ±1/4, 0. I'm dropping the inner product 1 from everywhere, so that doesn't show up. So Leach lattice, kissing configuration. its configuration is 4600, 7 design, -1 plus minus third, 0. Its kissing configuration is 891 points, 5 design, minus half, minus 8 quarter. By the way, here's an open problem. It's not known, it's conjectured that, so the Leech lattice has this curious property that its its kissing arrangement is an 11 design. And in fact, every shell of the Leech lattice, if you look at however many points it has, is an 11 design. So it's conjectured that 11 is the highest you can possibly go, that you can never have a 13 design, for instance. Or even, yeah, you can never have a 12 design for any lattice for every shell. That's an open problem. People don't know how to do it. 22. Here's a different one. So 552, 5 minus 1 plus minus 1/5. This is equiangular lines. Yeah, so there's, in real projective 22-dimensional space, there are 276 lines which make the same angle with each other. If you look at where they cut the, if you look at those points and their antipodes, then you get twice that, so 552 points, and they have, and that's universally optimal. And you can look at its kissing arrangement, you get 275 for minus a quarter and a sixth kissing. Sorry? So the equiangular lines happen in sort of, again, sporadic dimensions. So the question is, you're in real projective space and you want basically a collection of lines which all have the same angle with respect to each other. What's the maximum you can do? And it's I guess it's n plus 1 choose 2, if I remember correctly, because each one defines a projector, and basically the dimension of sim n, and each of them turns out to be linearly independent, all these projectors, so the maximum is n plus 1 choose 2. And so sometimes that's actually attainable, and this is one of those cases. So in some examples, and you can sort of write them down. I mean, it's a good question. I don't know off the top of my head, but probably there are reasonable ways to describe the configuration. I mean, yeah. I think you can look this up. I don't know off the top of my head. 162, 3 minus 2/7, 1/7. This is also kissing. So these are successive kissing arrangements of these guys. There's 22, 100, 3 minus 4/11, 1/11. This comes from the Higman-Sims group. And there are things which come from sort of affine geometries, q times q plus 1 over q plus 1. I won't describe these in detail, but f q plus 1, q plus 1 points. So there is a dimension, this is the number of points. It's 3 design, 4 if q is 2. And the inner products are minus 1 over q and 1 over q squared. These are isotropic subspaces in the number of isotropic subspaces in some 6-dimensional space. Q is a prime power. So these were, except for the 600 cell, these are all sharp configurations, meaning that the number of inner products times 2 minus 1 is less than equal to the design strength. And this table is exactly the table that Levenstein had for proving optimality as codes. But in fact, the same idea works for proving, well, I mean, sort of, you have to do some extra work, but you can, the ingredients are the same. The fact that you have a design of high strength is enough to show that they're universally optimal. So universal optimality of all of these proved that universally optimal paper, all except the 600 cell are sharp configurations. Recall that just means that there are 2m-1 designs. If m is inner products, m is the number of inner products distinct from 1. Okay, and 600 cell has some extra twist to it, which I won't go into. How do you prove that any of these are universally optimal? You use the LP bounds for energy minimization, which were proved by Uden for energy min. These were done by Uden. Okay, so what does it say? And so again, it's a very nice, elegant statement and proof. So f from 0 to 4 R be a potential function. And suppose that you have a polynomial which this I'm going to write as a function of inner product. This is a function, f you think of as a function of distance, this is a function of inner product, a poly such that h of t is less than equal to, f of the corresponding r, which is the square root of 2 minus 2t. So h lies below f, and I mean, once you make the change of variable, and the other thing you need is that h is positive definite, essentially. So I goes from 0 to d of alpha I g sub ni of t for alpha I greater than equal to 0, some degree d. So it's a polynomial. So you want all the coefficients, all the Gegenbaur coefficients to be non-negative. Then the bound says for any n-point spherical code, C on Sn minus 1, we have EF of C is at least n squared alpha sub 0, the 0th Gegenbaur coefficient, minus nh of 1. Okay, that's Uden's bound. All right. So let's just do the proof is essentially one line. So if you look at EF of C, it's the sum of f x not equal to y and C f of x minus y. So that's greater than equal to the sum over, again, x and y, x not equal to y, of h of xy, the corresponding inner product. Okay, that's because h lies below f. And okay, so then you can, so this is over x not equal to y, but let's add in the x equal y term and then complete the sum over all x, y, and c. So I'm going to write this as minus n h of 1. That's the diagonal. And then plus, that's what I don't have, so I'm going to add it back in, and then plus the sum of x, y, and c of h of xy. Okay, so far so good. And so this is equal to minus n h of 1 plus the sum I goes from 0 to, so I'm going to switch the order of summation. I'm going to plug in what h is. in terms of these and switch the order of summation. So I goes from 0 to d, alpha I, and then the sum over x, y, and c of g and I of x, y. Okay, I'll just switch the order of summation. Okay, and the point is each of these things, because you have positive definite kernels, are non-negative, so it's bounded by the I equals 0 term, and I equals 0, the gain bar polynomial is 1, so you get n squared times alpha 0. Okay, so this is at least n h of 1 n squared. That's it. Okay. So it's a very easy proof. So what's the idea of using this to prove universal optimality? So any questions about this proof? Using this to prove universal optimality is the following. Basically, you know that f has to lie below h has to whatever. So you're going to take in some potential function which is going to be completely monotonic of squared distance. You want an auxiliary function h is going to be a polynomial which depends on f. It has to lie below f, and at every, if you look at where the inequality actually happens, at every point which is an inner product between distinct points of the code, h had better equal f, otherwise you get slackness and you can't have a sharp bound. Okay, so h has to actually interpolate doubly, it has to lie below f, so roughly sort of it's going to look like this. So you're given some f and h has to lie below it and interpolate, so this is, and this is h of t. It has to interpolate doubly at every point of the code, every inner product that you see in the code, which is distinct from 1. Okay, and on the other hand, you need also that the thing is a design of sufficiently high strength. Otherwise, you don't get a sharp bound there. So the idea is the following. So you interpolate doubly. So that's just called Hermite interpolation. Normal interpolation, let's say Lagrange interpolation, is you interpolate singly at some function at some points using a polynomial. Here you interpolate doubly. You can do that at inner products not equal to 1. And also, well, also minus 1. But minus 1 you are allowed to interpolate singly. Okay, it can, because there's nothing beyond minus 1, you can do single interpolation at minus 1. Okay, you're allowed to do that. So this means h stays below f. So that's good. And the point is, if it's a strong enough design, then the degree of the polynomial you need to interpolate. What is the degree of the polynomial you need to interpolate? You're roughly imposing 2 conditions at every inner product. So it's going to be roughly twice the number of inner products, and that's why you see that you need a design of like 2m minus 1 roughly, approximately. Okay, so it's a strong enough design, then the degree of interpolating poly h of t is small enough so that all the g and I that are involved sum to 0 over the code by the design property, okay, by designicity. Okay, if it's a strong enough design that's going to happen. Okay, so then that automatically shows that you have a sharp bound as long as these coefficients alpha I are non-negative. So get a sharp bound as long as we can show all alpha I are greater than 0, which takes some work, okay? Which takes work. Okay, that's roughly the idea. And that's actually the majority of the work, to show that, the interpolation has some good properties. The interpolating polynomial has good properties. And actually, even in the Euclidean case, this paper that we wrote for universal optimality, the majority of the work is in showing these positivity properties. And once you have the idea, then the rest sort of follows, except this one technicality. Okay. So that takes care of all of these examples, except for the 600 cell. For the 600 cell, you have to use, it's not a, right, I mean, it's, the 600 cell is not a 12 design, so what happens is G12 doesn't vanish when you sum over the code, but G13 does, and so does G14, and so actually you get a little extra, and that's, you can use those to finish it off. That's the twist with the 600 cell. Let me make one more remark. There are some examples where you can show universal optimality. I haven't listed them in the table, but there are examples where you can show universal optimality for, where you could, by using SDP 3-point bounds, which you could not do by 2-point bounds. Okay, so SDP 3-point bounds for energy minimization exist. You can see paper of Henry Kohn and Ji-Chul Wu. So one case in which these bounds are sharp is, sorry, I'm proving universal optimality is actually projective examples, 7 points on RP2. And where do these 7 points come from? So if you take a cube on the sphere, that's 8 points, and you take its dual cross polytope, that's 6 more points, that's 14 points. You take the image in RP2, that's 7 points in RP2. Okay, so it's the image of sort of cube plus dual cross polytope. Which is also called, that thing is called a rhombic dodecahedron. Cube and its dual. I guess the cross polytope is just the octahedron. So that's one example where you can, I won't go through that, but these things exist. Okay. So next I want to say something about energy minimization and potential energy for Euclidean space, and there are linear programming bounds there as well. So bounds, which slightly different formulation. So recall again, I think I mentioned this in the first lecture or so. Recall that we're considering potential functions f of r of just Euclidean distance between every pair of points, and for C periodic configuration with some fixed point density. If you fix the point density, those points don't escape to infinity. Let's say C is the union of some translates, M translates of a lattice, lambda. We defined and potential function f, we define the potential energy EF of C to be the average value over points of C of the sum of the distance of f of f at the distance between x to y, where y ranges of all points of C not equal to x, y not equal to x. Okay, so you sum, you take, this is the local energy at x, and then you average over all x. I mean, that's, since it's periodic, that's really a finite average. This is 1 over m. You can write this as ij going from 1 to m, x belong to lambda, x not equal to 0, or I not equal to j of f of x plus vi minus vj. Okay. So, so that defines the potential energy, and there are linear programming bounds. So let me state them. It's a theorem. So these bounds for energy. This is in our paper on universally optimal distribution of points on spheres. It has a section on Euclidean space, and that's where we prove this. Given f a potential function, so now again we're going to have an auxiliary function, not necessarily a polynomial. So let h r into a real valued function r be a sufficiently fast decaying function such that h of x is less than or equal to f of x, f of the squared distance of the squared norm of x for all x. Yep. Question? Oh, how is this equal to this, or? Oh, okay. So C is a sum over right. M translates of this lattice, right? And so is this okay? That's EF of C is defined to be the average over all points in C. So what you do is you want to sum over all pairs of points in C. So for every pair of point in C, you want to take the distance. You want to apply the potential function, and you sum this over. But you don't want every distance is going to show up infinitely many times. Like if C was a lattice, you would see, every vector showing up infinitely many times among the differences. So you don't want to do that infinite sum. I mean, you want to see every distance in that sense only once. I mean, you want to remove the redundancy. That's why you take an average. So for every point of C, you take its distances from everything else in C, which is what this sum is doing, and then you average over all points in C. That's a finite average because if you translate by an element of the lattice, it doesn't affect, I mean, everything can translate, so it doesn't affect anything. So it's really a finite average over the m cosets, I mean, the m translates that you have, and you get, so here, basically, your x that your sum, the x is vi, and, sorry, the x is vj, you're summing over j. I mean, this inner sum is, this outer sum is over j, and then sort of you're summing over all points of C, so that's x plus vi. But you don't want x plus vi to equal vj. I mean, you don't want that thing to be 0, which is what this is doing. So either x is not 0 or I is not j. So it's just, the sum is over all ij going from 1 to m, and all x in lambda, such that x is either not 0 or I is not j. I mean, if x was 0 and I was j, that's exactly the situation where you would get 0, you would get the 0 vector showing up. No. If f is decaying fast enough, then it's not infinite. You see everything, finite number of times. Does that make sense? Yeah.
Distances that are 1 are being counted more than distances that are 2. Think of it as average in the space.
Okay.
The distance where distance 1 occurs many times in any finite box than other.
Okay. It is, yeah. I mean, yeah. I mean, right, for any finite number of distances, right, 1, 2, or whatever, if you take a large enough ball, then you can convince yourself that the discrepancy between the number of times you see the distance 1 and the number of times you see the distance 2 is actually not, is marginal compared to the volume of the ball. This is something you can think about, but it's not, trust me, this is okay. And I think I gave some kind of argument in the first lecture. And if that wasn't enough, then you can sort of look in the paper and we sort of deduce this from that. It's straightforward. As long as f is reasonable decay, everything converges, and those notions are actually equal. It's not too difficult. Okay, so let me keep going. So your auxiliary function, not necessarily a polynomial, you want that to be less than or equal to f of x, the norm of x. And you want the Fourier transform of the auxiliary function to be non-negative for all. So in some sense, if you think about this, this is combining both the sphere packing Cohn-Elkes bound and the Euden's energy minimization bound. What is it doing? It's saying you need to interpolate f, you need to stay below f, and on the other hand, you need to be positive definite. So it's just sort of, it's quite similar. In the other situation, in the spherical code, in the sphere packing case, you wanted h to be non-positive beyond a certain point. So the potential function is really a potential well, and you can have an analog in the spherical code case. But anyway, this is sort of the appropriate analog. If you find such an auxiliary function, it's saying then EF of C for any periodic configuration is bounded below by rho. Rho was the, did I say delta? Point density, fixed point density. I left it open. Okay. Rho, okay, is bounded below by rho h hat of 0 minus h of 0 for any periodic configuration C with density delta. With density rho. Okay. Well, this is the point density. Point density rho. Okay. So I'm going to omit this proof. It's similar to all the proofs that you've seen, and it's a few lines, but I think we state in fairly wide generality, and we only assume that H is the Fourier transform of something, and so on and so forth. So you can see the paper for the proof. Or you can do the proof yourself. It's not very hard. Let me just say, when would you expect equality? Oh, sufficiently fast decaying function. I mean, in all our examples, H is going to be a Schwartz function, so we don't have to worry, but yeah, as long as it's decaying fast enough, everything is good. Okay, so omit proof, see that paper, but let me just note, similar to others we've seen. But let me remark, so to obtain when would you get equality? So to obtain a sharp bound, what do we need? We need that H actually equals F. This is something that you see when you write out the proof, which I'm not doing, but I'm just going to say what the result is. So so H has to equal F at all x of the form y minus z, where y and z are elements of periodic configuration not equal to each other, as well as, so in particular, if the periodic configuration is just a lattice, then it's saying H has to interpolate at all vector lengths away, which are not 0. Okay? H has to equal F at all those vector lengths, as well as that you also need that H hat vanishes at all non-zero points of the dual of the underlying lattice. I mean, you can read out exactly what the condition is that you need, but it's similar to the kinds of things you've seen in the sphere packing case. Okay, and this is sort of H hat vanishing. Think of that as yeah, you think of that as a sort of what do you want to think of that as? Yeah, you think of that as sort of a condition on on the design on the interpolating polynomial over here that we had, that either it's a design or the corresponding coefficient has to vanish. Either the Gegenbauer polynomial sums over 0 or the corresponding coefficient has to vanish. So anyway, you get this condition on H hat as well. Okay, so I want to go over a little bit what happens in low dimensions if you do energy minimization. Okay, so what happens? What do we observe sort of experimentally? What do we observe for energy minimization for low dimensions? So it's sort of analogous to if you did experiments, the experiments that I described where you had 5 points, 6 points, etc. You observe some interesting phenomena. And again, we're going to consider, we can consider either 1 over inverse power laws, or more generally completely monotonic functions of squared distance. And in this case, there's a nice description. The cone of such functions is spanned by Gaussians e to the minus pi. I'm going to write them as e to the minus pi c r squared, where c is non-negative. Okay, so this is e to the minus k x is completely monotonic function of x, and basically every completely monotonic function is an integral of such things. That's an easy exercise. So these if you're looking at squared distance, these things basically span the cone of completely monotonic functions. So these are the ones that you need to consider. And we just say that you can get 1 over r to the k from this as a Mellin transform of Gaussians. Okay, so all right. So before I give you the experimental results, let me just say that C is universally optimal as before if it minimizes every such Gaussian among all periodic configurations of the same density, right? Namely the density of your configuration, so density of C. Okay, so among all configurations of the same density as C, if this is the minimum, global minimum for every Gaussian energy, which is a very, very strong condition, then you say it's universally optimal. So, okay, let's see what happens in some small dimensions. So, okay, dimension 1. So Z, it turns out to be universally optimal. And this is, we proved this. I mean, this is not too hard. Okay, so it's proved in. Okay, dimension 2. A2 is conjecturally universally optimal. We conjectured this, and we still don't have a proof. It's not proven. Okay, dimension 3. This is where we start having a little fun. So we know very little rigorously, very little known rigorously. So some computational experiments, the ones that I'm going to talk about, are described in a paper, Henry Cohn, myself, and Akhil Sherman, and it's called Ground States and Formal Duality relations in the Gaussian core model. And it's in actually a physics journal, so it's in Phys Rev E or something. Okay, anyway, you can look this up. This is all online. This discusses. We did computational experiments where we looked at periodic configurations with a small number of translates, and we just ran simulations and to see what happens. Results. So what happens? So in dimension 3, what seems to happen is that D3 is optimal for C going to infinity. So C is this exponent for the Gaussian. So if it's very steep Gaussian, then it looks like sphere packing. And again, you can convince yourself that it should look like sphere packing. So D3, which is the face-centered cubic, the sphere packing answer should be optimal. And it is, numerically, while its dual is optimal for C going to 0. So in fact, there's a duality in this thing. So if you take the Fourier transform of this Gaussian, you get a 1 over C. You get a Gaussian with 1 over C. And it turns out that the energies of a lattice with respect to this Gaussian is related to the energy of the dual lattice with respect to that dual Gaussian, that Fourier transformed Gaussian. So you expect something like this, and it seems to be true. No, unfortunately, no, because the problem is you could have things, there's no sort of general analog of, so lattices have a dual, but periodic configurations in general don't have a dual. So problem is you could have a periodic configuration that, a priori you could have that. Doesn't seem to be the case, but. So the crossover sort of should be at C equals 1, which is sort of self Fourier, dual, but in fact, there's something which the physicists call the Maxwell double tangent construction. Sounds fancy, double tangent construction. It just means that the potential energy is convex as a function of C. Potential energy as a function of C, and it turns out that if you have something at small c and something in large C, you can sort of, take the line joining them, etc., and sort of that gives a better result. Something about convexity. So what's in fact better than either of them at C close to 1, so is phase coexistence. So phase coexistence is better than either near C equals 1, okay? Which means the following horrible thing: you take some parts of D3 and some parts of D3 dual at the same density, and you mix them together. Okay, I mean you can sort of take a large cube and take another large cube, etc. So that's phase coexistence. That's better than either of them at near C equals 1 for energy. Okay, all right. Let's keep going. Dim 4. D4 is probably, not provably, probably universally optimal. But what I can definitely tell you is, but this is not provable by LP bounds for sure, by linear programming bounds. Okay, linear programming bounds certainly are not going to get you there. Maybe semi-definite or something will get you there, but this would be amazing if one could show it. We don't even know that it's optimal for sphere packing. Okay, let's keep going. D5, 5 dimensions. So here we get a chance to revisit some of these tight packings that I talked about in the first lecture. So one of the uniform tight packings is better than D5, namely, here's one. So D5, remember, is so the tight packings in 5 dimensions correspond to sequences on sort of 4 quaternary sequences, coloring the integer line with 4 colors. So D5 turns out to be AB, AB, dot, dot, dot. There's something which is called lambda 5-2. This is Conway and Sloan's notation. So that's A, B, C, D, A, B, C, D, dot, dot, dot. And this is better as C goes to infinity than D5, okay, for energy. But in fact, this is not the best one. So simulations improves on D5, improves on lambda 5-2. So we get elements of the following family. For large or small c. So the family is this. So let dn plus be dn union the translate by the all halves vector. So this is it's not a lattice because, right, I mean, it would be a lattice if you had even dimension, but it's not. Okay, so that's called dn plus. It's a periodic packing with 2 translates, as a periodic configuration with 2 translates of dn, and then you can define dn plus a scaling by alpha where you just scale the last coordinate, so x1 dot xn, xn minus 1, and alpha xn for x1 dot xn in dn plus. So again, this is just a shear of the dn plus periodic configuration, and so d5 plus is what we're going to look at. So d5 plus alpha is you can think of it as a deformation of in fact, it's a deformation of lambda 5-2 with sort of compression factor alpha over 2. So by which I mean that lambda 5-2 is actually part of this family, is d5 plus of 2. Okay, so what happens? So we seem to get elements of this family. So these seem to optimize, except around c equals 1, where again you have phase coexistence. We get And let me just make a little note. I'm not going to explain this, but you can define something called formal duality for periodic things. Not quite dual, but so dn plus. So these are examples of formal duality, hence the name of the paper. So dn plus of alpha is formally dual to dn plus alpha. So I don't have time to go through what that means, but you can read the paper. It's a short paper if you really want. Okay, so then dimension 6, what seems to happen is you get E6 for C going to infinity. You get its dual for C going to 0. And in between, what do you get? So in between, you get a periodic packing, periodic configuration with 4 translates of D3 plus D3. So that's 6-dimensional lattice, and again with scaling. So again, there's a continuous family, and let me just describe what it is. So there's P6, which is D3 plus D3 union with translates these 3 vectors. So the 0 translate is 1, and then 3 more. So the all halves vector is 1, and then there's 1, 1, 1, minus half, minus half, minus half, and then there is minus half, minus half, minus half, 1, 1, 1. Okay? So that's a periodic packing, and that seems to, and you can define P6 of alpha to be, take P6 and you scale first 3 coordinates by alpha, and last 3 by 1 over alpha. Okay, so that turns out to be turns out to be self-dual, self-formally dual, and you seem to get that in the middle, away from sort of infinity or 0. Numerically, that's what seems to happen. Okay, last few dimensions, and then I'll go on to sort of the sphere packing stuff. Let me see, I still have some time. Okay, so dimension 7, you get D7 plus of alpha at all densities, at all C. And around C equals 1, in some interval around C equals 1, you seem to get D7 plus without any scaling. I mean, where alpha equals 1, okay, itself. So in particular for C going to infinity, you get D7 plus of square root of 2, which is another one of these tight uniform packings that Conway and Stone discussed, lambda 7, 3. And for C going to 0, you get D7 plus of 1 over the square root of 2 by duality. Okay, then dimension 8, E8 is universally optimal, which is now proven. So we're going to describe tomorrow. And in dimension 9, so there's lots of, the point of this, there's lots of fascinating stuff going on, and most of it is unproven. And it would be great to have either more numerical results or, or some proofs. D9 plus seems to be, is somewhat counterintuitive, seems to be universally optimal. Though I would bet that we have no chance of proving it within our lifetimes. Anyhow, so lots of fun things happen in high dimensions, most of which we don't have a clue how to prove. So in the last 15 minutes or so, maybe I'll go slightly over time. I want to start describing the proof of the sphere packing solution in 8 dimensions. So Marina's proof, and if I have time, I'll say something about the 24-dimensional case as well. I want to sort of motivate a little bit what's going on, and I will try to do it without saying much about modular forms, okay? But the point is, if you look at the paper is, both the papers, they're short, elegant, easy to read, and easy to verify locally, right? And it's this sort of thing where you sort of go through the paper, everything looks right, et cetera, you're convinced it's correct. But where did the idea come from? That's the key question that people ask. And so maybe I'll try to give some kind of intuitive understanding of where these things came from. So start proof of sphere packing. AT, this solution. So recall, here's what we want. We want a magic function. Which looks like this. So here's the function f. It should be a radial function of distance. So it's a radial function. And so you can think of it as a function of one variable. It should cross to start from something positive, it should cross the x-axis at square root of 2, which is the smallest non-zero vector length in E8, and it should stay below that, below the x-axis after that, except it has to, as I said, if you want sharpness in the linear programming bound, it had better vanish at all the vector lengths of E8. Okay, so at square root of 4, which is 2, it has to vanish at square root of 6, etc. Okay, all right. So it has to do that, and it's not clear how you're going to make such a function, but we'll see. We'll try something, and it's Fourier transform. So that's f. Fourier transform. Fourier transform has to look like this. The Fourier transform stays above 0 all the time, okay, but it has to touch again at all these points, square root of 4, square root of 6, ... okay? This is f hat. So you need to manufacture a function which satisfies these two properties. That's at least what you need. All right, so Marina starts with the ansatz. Here's what we're going to say. The key thing is to place the square, place all the zeros where they are. Okay, so what's a function which does that job? So has zeros at all the square roots of the even integers. And that's one key property of the E8 lattice that we're using, that its vector lengths correspond to the square roots of all the even integers. Okay, so here's one function that does that. So some constant, in this case she chose -4, but here's the key function, okay, sine squared pi r squared over 2. So this just means sine of pi r squared over 2 squared. I mean, we're just writing it in the normal form. So what does that do? And then times something, okay? So I'll fill that in, but let's see what this function does. So sine of pi x vanishes whenever x is a multiple of, x is an integer, right? So sine of pi x over 2 is going to vanish whenever x is an even integer. That means r squared is an even integer. So it's going to vanish at every one of these points except to order 2, okay? Because I have a sine squared here. So that's what sine is doing. I'm going to multiply this by something. So this is, and then I need to make it sure its Fourier transform also has good behavior. Okay, so this times the integral from 0 to I infinity of phi 0 of -1 over z squared. So forget about what exactly is going in here. I'll tell you what the key parts are. So pi I r squared z. Okay, so phi 0 is going to be a function of a complex variable, so some single value, upper half plane, and you're going to integrate on the contour from 0 to I infinity. So you can sort of make the transformation z equals it, and then this becomes phi 0 of -1 over it. Whatever is some function, this is going to be some real valued function of t times of it squared times e to the minus pi r squared t times I dt, right? Well, not exactly real valued, but I mean, there's going to be an I that this is going to be I times something real. Anyway, so the point is, this thing is a Laplace transform of this function where r squared is your Laplace parameter, okay? And so you're going to get something which possibly has poles. When you take Laplace transforms of functions, you may get, depending on the behavior at infinity, you might get a pole of this function, and you need a pole which is going to cancel your double pole at square root of 2, okay? On the other hand, the key thing is you need its Fourier transform to be well behaved, to have the same form, okay? That's the other key thing that you need, and we're going to try to arrange that. All right, so let me just say, note that. So what have we deduced so far? So note that sine squared pi r squared over 2 has double zeros at square root 2, square root 4 dot. So need to have simple pole at square root of 2, and well, sort of, double pole at 0, so to speak. I mean, the way we're going to define it is by analytic continuation, so we don't really need to worry about a double pole at 0. But anyway, and you need the Fourier transform to have suitable properties. In particular, you'd like it if the Fourier transform was also some kind of Laplace transform of a complex function or a linear combination of things like that. Okay, so all right. So what we're going to do is, first thing is, this thing is going to be defined for r sufficiently large in this way. So for r sufficiently large, we need to define it for every r. So what we're going to do is we're going to transform this a little bit and just make it a sum of contour integrals. So you write minus 4 sine squared pi r squared over 2 as the following. So this is trigonometry, so minus twice 1 minus cosine of pi r squared. So remember that cosine of 2 theta is 1 minus 2 sine, 1 minus 2 sine squared theta over 2. So this is true. And then again, this you can write as cosine is e to the pi I r squared plus e to the minus pi I r squared over 2. So you can write this as e to the pi I r squared plus e to the minus pi I r squared minus 2. So that's the first transformation. So, yeah. Yeah, so what's going to happen, so for instance, right, so this integral is not going to converge if r is too small. Like, you're going to get a pole here, which looks like 1 over r squared minus 2, so if it's less than that, you have a problem. Yeah. So you need to, basically analytically continue, and that's what I'm going to do now, writing it as a sum of different integrals. But the point I want to make is this ansatz is sort of reasonably well motivated. I mean, here's the key function that you want, and you want to multiply it by some, some factor that maybe gets rid of one pole, and of course, it's a little bit of a leap of faith. You have to make a leap of faith and say, that should be some kind of Laplace transform of a complex valued function. The question is, what properties does that complex valued function need to satisfy? We'll see that it has to be some kind of a modular form. And I won't say too much, but Mahesh will sort of define what modular form is and what, it'll be clear what kind of things we're going to need. Okay? So in particular, what happens is, so we write f as integral from 0 to I infinity. So pull this inside, this factor inside the integral, and you can rewrite this as pi 0 of minus 1 over z, z squared, e to the pi I r squared z. That's the stuff that's already there, and then times e to the pi I r squared plus e to the minus pi I r squared minus 2 dz. Okay, so now let's split this up into 3 integrals. or 3 terms. How much do I have left? Let's see. A little bit, but I hope, is everybody okay if I go over for a little bit? Well, this is sort of fun, so, yeah. Maybe I'll go for 15 minutes, and we'll see where we get, okay? And then we should really have our coffee. All right, so, so this is integral of 0 to I infinity of e to the, so phi 0 of minus 1 over z squared, e to the pi I r squared z plus 1. So yeah, so this times this gives you z plus 1 and plus e to the pi I r squared z minus 1 minus 2 e to the pi I r squared z dz. Okay? And so then this is, then what we're going to do is we're going to shift, make a change of variable. So for the first integral, you set z equals, z prime minus 1. You can shift that. So then that becomes the integral from minus 1 to, sorry, what do I want? Yeah, you set, you said z plus 1 equals z prime. So then z prime goes from 1 to I infinity plus 1 of, so you get phi 0 of minus 1, and z is z prime minus 1. So you get, I'm relabeling z prime to z in the same step. Sorry, this is sort of 2 steps combined into 1, but I'm sure it won't confuse people too much. E to the pi I r squared z. That's what the first term gives you. And then the second gives you minus 1 to I infinity minus 1, phi 0 of minus 1 over z plus 1, z plus 1 squared, e to the pi I r squared z dz. And then the last one is just minus 2, integral 0 to I infinity of phi 0 of minus 1 over z squared, e to the pi I r squared z. All right, very good. So now the point is, okay, we're going to assume this goes from 1 to I infinity plus 1. So you have one contour which goes from 0 to I infinity, and contour which goes from minus 1, I infinity minus 1, 1 to I infinity plus 1. And the point is we're going to deform the contour. We're going to, if r is large enough, this whole thing decays at infinity. So we can sort of replace I infinity minus 1 by I infinity. Okay, so you can sort of deform the contour. So first go from here to here, and then you can sort of really go from here to I and then I to I infinity, which is what we're going to do. Okay, and that's reasonable. I mean, all these things won't have poles. So assume we can deform path of integration as, so let me just say that, we're going to assume that phi 0 has no poles in H, in the upper half plane, except it may have a pole at infinity. I mean, we'll have to worry about that at some point. You may have poles, at 0, at infinity, but nothing in the upper half plane. And that will be apparent from the actual thing that we write down, the formula that we write down at the end for phi 0. Okay? So then this becomes, get f of r is, so you get minus 1 to I. So I'm going to deform, first go from minus 1 to I infinity, and then go from minus 1 to I, and then I to I infinity. So I'm splitting it up all in one step, so phi 0 of minus 1 over z. I'll take this one first. Okay, minus 1, z plus 1 squared, e to the pi I r squared z dz, plus I to I infinity of the same thing, okay? I'm just of the same integrand. I'm not going to rewrite it. And then plus 1 to I infinity, sorry, 1 to I of phi 0 of minus 1 over z minus 1, z minus 1 squared to the pi I r squared z dz, plus again integral from I to I infinity of the same, of this thing, and then minus twice integral from 0 to I of phi 0 of minus 1 over z, z squared e to the pi I r squared z dz, plus, again minus 2 of integral I to I infinity of the same thing. Okay? So now the point is, you have these integrals which go from, which follow the same path, so you can combine the integrands. And what happens when you do that? So let me make a bracket around this and just say the combine the three bracketed integrals. And what you get? You get integral of I to I infinity of, some expression. So let me write it as following. Okay, so let me write it as delta squared. I should not have this. Use let me call it this delta. I'll say what this is in a second. So delta z squared of phi 0 of minus 1 over z, z squared times e to the pi squared z. Okay, what is delta z? Delta is the difference operator. I didn't want to write capital delta because that's the modular form, but delta z takes a function, so it takes a of z to a of z plus 1 minus a of z. Okay, hopefully I did this right. I mean, evaluated it, yeah, I guess. Evaluated it. This is, let me just say, z minus 1. Yeah, this is, okay. Let me just write it out. Sorry. Yeah, no, let me write delta z squared of phi 0 of minus 1 over z, z squared, but evaluated at z minus 1. I think this is correct. And then e to the pi I r squared z dz. Because the second difference operator, that's what's showing up, right? It's, if you take the second difference of a function evaluated at z, you just get f of z plus 2 plus f of z minus 2f of z plus 1, I believe. Right? So that's what's happening here, except you're shifting by minus 1. So it's f of z plus 1 plus f of z minus 1 minus 2f of z. And the point is, okay, this thing now has to satisfy a certain property. So if delta squared of phi 0 minus 1 over z, z squared, whatever this function is equal to 2 phi 0, this is what we're going to postulate, then it follows, and also, right, also phi 0 of z plus 1 equals phi 0. So if phi 0 is invariant under translation by 1, then it follows that f of r is minus 1 to I, phi, is these three integrals plus the new one that we're going to get, so plus integral 1I phi 0 minus 1 z minus 1 z minus 1 squared e to the pi I r squared z dz, and then plus this final thing simplifies to integral from I to I infinity of just phi 0 of z e to the pi I r squared z dz. Okay, so that too comes from that too. Okay, and right, it turns out that this follows, this property, this key property follows because from phi 0 being what's called a quasi modular form, quasi modular of weight 0 and depth 2. Okay, so this you will see these terms being defined in the next lecture, and this is another property that you see in modular form theory. So when you translate by the operator t, which takes z to z plus 1, you should be invariant, or you should multiply by a suitable factor depending on the weight. Here the weight is 0, so it's just saying it's invariant. Okay, so and this will be a quasi-modularity property, and you see that this is roughly telling you what's happening under the operator S, under the group element S, which takes z to minus 1 over z. So modular forms is pretty motivated. I mean, this tells you roughly what you need to first convert this into, to get an analytic continuation. And this is not the full story, because you need one more thing, which is the Fourier transform. You want the Fourier transform, so let me just do that, and then we'll pause. So let me just say, so the key thing you need is the Fourier transform. Must be nice. Must be something of the same type that we can control. And what we're going to make is that, so we'll try to make a +1 eigenfunction for the Fourier transform, which means, so any function you can decompose as a +1 and -1 eigenfunction of the Fourier transform. The Fourier transform has period 2, so that means you can write any, so whatever function that you're looking to plug into the linear programming bound, you can write it as a sum of two components, which are both eigenfunctions. One is a +1, one is -1 eigenfunction, and we're trying to make the +1 eigenfunction here, which means what we want is that when you compute f hat, so this is, you think of this as sort of, right, this is really f of x, which is, you know, yeah, you'll see in just a second. So let me try to compute the Fourier transform, and you'll see what's going on. The reason you write it like this is, what's going to happen is things are going to switch, and you'll see that it's actually an eigenfunction of the Fourier transform. That's the point. So let's do it. So Fourier transform. So this gives us another, that'll give us another key requirement. So let me just say the Fourier transform of, you're going to apply the Fourier transform on R. Okay, so R is the absolute value of x, or the length of x. X is your variable in Euclidean space. You're going to go to y. That's the Fourier transform variable. And so that's the only place it appears. In this formulation, there's no sine pi r squared, etc. So you just have to transform that one exponential. Okay, so and what's the transform? It's the following thing. So Fourier transform of pi I x squared z as a function of x. When you Fourier transform it, you just get z to the -4th. This just comes from the volume element, and then pi I y squared, and then this coefficient, I mean, just as in the one variable case, if you have a here, or we had c there, it went to 1 over c, it's going to go to -1 over z. Okay? And the reason it's -1 over z is because it has to do with the I that's showing up here. Okay? But that's the Fourier transform of this variable. And so when you transform, so f hat of y turns out to be a sum of integrals which look like this, -1 over. So the first one, you just repeat the same thing except you transform this term. So you get phi 0 of -1 over z plus 1, z plus 1 squared, times z to the -4th e to the pi I y squared -1 over z dz, okay, plus ... And then you make a change of variable. You want z in the numerator, so change of variable. So you set z equals minus 1 over w. And what happens? So dz is 1 over w squared dw. And z to the minus fourth comes w to the fourth, etc. So what you get is the following thing. So let me just say, so what is minus 1 over z plus 1 is minus 1 over w plus 1, which is, I'm just computing the first term out. This is minus w over w plus 1, which is 1 minus 1 over w minus 1. Okay? You can compute that out. So f hat of y then becomes a sum. So the first term looks like minus 1 to y, phi 0 of 1 minus 1 over w minus 1, minus 1 over w plus 1 squared, w squared. So the w squared comes from w to the fourth times 1 over w squared, e to the pi I y squared w dw. And okay, what does this mean? So then this becomes yeah, so this so let me see if I have this right. Z plus 1 squared. So this becomes just w minus 1 squared. You combine these two, and phi 0 is invariant under translation by 1. So this is phi 0 of minus 1 over w minus 1. And you see that you now exactly this term, the Fourier transform of the first term, is exactly equal to the second term over here. Okay? And similarly, the Fourier transform of the second term becomes the first term. If you do these ones, you get, you know, the integral goes from I infinity to I, and then so that goes to this and this goes to that. Okay, so that's roughly how this works. So you've just produced a Fourier transform. So this produces a plus 1 eigenfunction. So and we have just figured out what properties we need for phi 0 to be able to do that. And let me just say that, you know, if you look at the asymptotics of phi 0, you see that you get the right pole and so on, and that lets you get the right form of f. So one more thing, let me just say, and then we'll stop. It's actually pretty easy to write down very explicitly the eigenfunctions in the 8 and 24 dimensional cases. Let me just do that, and then that'll be it. So phi 0 equals, this is the plus 1 eigenfunction in the 8 dimensional case. It's E2, E4. I don't think this is in the paper, is written quite this way in the paper. It's E2, E4 minus E6 squared over delta. That's it. Okay, it's very easy to write down. And you'll see these functions showing up in the next talk. And on the other hand, the minus 1 eigenfunction, let me just say what it is, and then I'll tell you what the terms mean. So psi turns out to be w cubed times 5uv plus w twice w squared over delta. So pretty straightforward to write down. What are w, uv, and w? So let me just say, so u equals theta 0, 0 to the fourth. V equals, I'll say what these terms are, so I'm sort of going top down. V equals theta 1, 0 to the fourth, and w equals theta 0, 1 to the fourth, where theta 0, 0 is the sum over n in z of e to the pi I n squared z. Theta 0, 1. So these are half integral weight modular forms for gamma of 2. All these words, if you don't know them, you'll see them in the next lecture. And then z of minus 1 to the n, e to the pi I n squared z. And theta 1, 0 is sum over n in z, e to the pi I n plus half squared z. So these are modular forms weight 1/2 for gamma of 2. I didn't motivate exactly why we get this, but again, if you write down the condition for the Fourier transform to be minus of what it is, you will see that you get similar conditions for psi that pin down which way, which space of modular forms you need to be in. Here you don't need quasi-modular forms, but you do need to go to a subgroup and look at these. So these things are all, since they're fourth powers, they're weight 2 modular forms. And eventually then you get, you get psi by this formula. Let me just note that U equals V plus W. This is called the Jacobi identity. I mean, that's not obvious from the way I've written down these things, but it's a nice identity. And so that's the 8-dimensional case, and completely explicitly you can write down. Let me just finish. Sorry to keep going, but I'll just write down two more lines: the plus and minus eigenfunctions, the 24-dimensional case, and then we'll stop. Okay, so plus 1 eigenfunction is phi equals 25. Question? 25 e4 to the 4th minus 49 e6 squared e4 plus 48. There are lots of coincidences between these numbers. You might have fun exploring some of them. E2 plus minus 49 e4 cubed plus 25 e6 squared e2 squared divided by, now you need a square of delta in the denominator, and then psi equals w to the 5th 7 uv plus 2w squared over delta squared. And so that defines these functions. You have to take suitable linear combinations, and you get, which you can figure out from the input, what linear combination the plus and minus 1 eigenfunction you need to take. When you plug in, you get a sharp linear programming bound. You still have to show that the functions look like what I said, that they don't have any extra sporadic roots. But that, as of now, that takes computer verification. But it would be very nice to sort of get sort of more elegant hand proof, which didn't use any computer checking. Some indications are in, let me just refer you to Westerle's talk in Seminar Bourbaki. It's called Densité Maximale de Empilement, I guess, backing the sphere on dimension 824. Okay, that's Westerle's talk, and I think he goes part way towards making the proof sort of computer free, but not all the way, I think. Anyway, that's it. So sorry to go over time. Tomorrow morning we're just going to go with sort of how these generalize to give you energy minimization and universal optimality. Thanks.